Welcome back to our second lecture in the fifth week of our course Analysis of a Complex Kind. Today we'll learn more about complex integration, we'll look at some examples, and we'll learn some first facts. Remember, this is how we define the complex path integral. Given a smooth curve gamma and a complex valued function f that is defined on gamma, we define the integral over gamma f of c dz to be the integral from a to b f of gamma of t times gamma prime of t dt. So this second integral can be broken up into its real and imaginary parts and then integrated according to the rules of calculus. Let's look at some more examples. Suppose gamma of t is given by 1 minus t times 1 minus I, where t runs from 0 to 1. Let's get a quick idea of what this path looks like. When t is equal to 0, gamma of t equals 1. And when t is equal to 1, gamma of 1 is equal to 1 minus I, in other words, I. So that is gamma of 1. And what happens to the path in between? In between, there's a linear relationship between x of t and y of t. If we write gamma of t as x of t plus I y of t, then the real part is 1 minus t, and the imaginary part is simply t. So y is equal to t, x is equal to 1 minus t. They're linearly related, so we just get this line segment from 1 to I. Let's see what the integral does. The integral over gamma f of z dz, by definition, is the integral from 0 to 1, these are the bounds for the t values, of the function f. The function f of z is given by the real part of z. So we have to take the real part of gamma of t and multiply that by gamma prime of t. What is gamma prime of t? Gamma prime of t is, well, the derivative of 1 is 0. Derivative of minus t times 1 minus I is minus 1 minus I. So remember, the path integral over gamma f of z dz, is defined to be the integral from a to b, f of gamma of t, gamma prime of t dt. That's what we're using right here. So the integral over gamma f of t dz is the integral from 0 to 1. F is the function that takes the real part of whatever is put into it. We're putting gamma of t into it, that's right here, and then we multiply by gamma prime of t. So this is the integral we have to evaluate. Let me clear the screen here. To evaluate this integral, we need to find the real part of 1 minus t times 1 minus I. But the real part is everything that's real in here. So what's real? 1 is real, minus t is real. But then if we multiply through, we have a plus t times I, that's the imaginary part. So the real part is 1 minus t. And we're multiplying by minus 1 times 1 minus I, which is the same as I minus 1, but that's a constant. We pull that out of the integral. So here's the I minus 1, and then the integral of 1 minus t dt. And the derivative of 1 minus t is t minus 1 half t squared. We evaluate that from 0 to 1. So in the end, we get I minus 1 times 1 minus 1 half times 1 squared. That's the integral evaluated at the upper bound. And if you evaluate it at the lower bound, we get a 0. So altogether, 1 minus 1 half is 1 half. The value of the integral is I minus 1 over 2. Let's look at the second example. Let gamma of t be r e to the it, where t runs from 0 to 2 pi. We know that that parameterizes a circle of radius r. Gamma prime of t, we also know what that is. That is r I e to the it. And the function f we're looking at is f of z is the complex conjugate of z. Let's find the integral over gamma f of z dz. F of z is the complex conjugate, so it's integral over gamma of the complex conjugate of z dz. And we know what we have to do is we have to look at f of gamma of t times gamma prime of t and integrate that over the bounds from 0 to 2 pi. So we get the integral from 0 to 2 pi. This is f of gamma of t. And since gamma of t is r e to the it, we have to take the complex conjugate of r e to the it. So here's the complex conjugate of gamma of t, and then we have to multiply by gamma prime of t. The complex conjugate of r e to the it, we looked at that a while ago, that's r e to the minus it. And the derivative of gamma is r I e to the it. So I have an r and another r, which gives me this r squared. And there's this I, we can also pull that up front. And what's left inside is e to the minus it times e to the it. Those two cancel each other out. So the integral is just over, if you want to put a 1 there, you could, dt. And antiderivative of 1 is t. And we need to plug in the upper bound and subtract from that the value of the lower bound. So at the upper bound we get 2 pi, at the lower bound 0. So the value of the integral is 2 pi times r squared I. If we rewrite that, we could write that as 2i times pi r squared, and pi r squared is the area of this disk. So it turns out this integral is the area of the region that is surrounded by the curve. And there's actually a more general fact that says if gamma surrounds an asymptotically connected region, then the integral over gamma z bar dz is the area of the region it surrounds. I want to remind you of an integration tool from calculus that will come in handy for our complex integrals. Suppose a, b, and c, d are integrals in R, and h is a smooth function from c, d to a, b. So here's a, b, and there's c, d, and h is a function from c, d to a, b. F is a continuous function defined on a, b. Then integration by substitution says that you can integrate f of t dt from h of c to h of d, so h of c and h of d are some points in this integral, where f is defined, or alternatively, you can integrate from c to d, the function f of h of s, multiplied by h prime of s ds, and these two integrals are the same thing. Let's look at an example to remind you how this goes. Suppose you wanted to integrate from 2 to 4 the function s squared times s cubed plus 1 to the 4th power ds. We recognize that that is an integral of the form on the right, where this is my function f of h of s. If I set h of s to be s cubed plus 1, so this right here is my h of s, then here I see h of s to the 4th power. And over here, I see almost h prime of s. h prime of s is 3s squared. So I need an extra 3 there, and then that is h prime of s. But I can't just put a 3 there, I need to make up for that. So put a 1/3 in front of the integral, and all of a sudden this integral here is of the form f of h of s times h prime of s ds, where f is the function that raises its input to the 4th power. By integration by substitution, this integral is the same thing as the integral from h of 2 to h of 4, so h of 2 to h of 4 of f of t dt. F is the function that raises its input to the 4th power, so f of t is t to the 4th, and I integrate dt, and this 1/3 needs to remain there, because that's outside of the integral, that doesn't affect what's happening with my transitions on the inside. So now I need to find the integral of h of 2 to h of 4 t to the 4th dt. What is h of 2? I need to plug in 2 for s right here. That is 2 cubed plus 1, that's 9. What is h of 4? What's 4 cubed plus 1? That's 65. I need to find 1/3 times the integral from 9 to 65 of t to the 4th dt. And the derivative of t to the 4th is 1/5 to the 5th, so we need to evaluate that from 9 to 65, so the result is 1/15 times 65 to the 5th minus 9 to the 5th. we can use integration by substitution to find out that the complex path integral is independent of the parametrization that we choose. To make precise what I mean by that, let gamma be a smooth curve defined on an integral AB, and let beta be another smooth parametrization of the same curve given by beta of s is equal to gamma of h of s, where h is a smooth bijection. So let's look at this picture. Here's the integral from a to b, and here's the integral from c to d, and h is a smooth bijection between these two intervals. Gamma is a curve defined on AB, so here's that curve gamma. But I'm also looking at a curve beta that's given by beta of s is the same thing as going over with h and then applying gamma. So gamma of h of s is the same as beta of s. Now suppose I have a complex valued function that's defined on gamma, then what is the integral over beta f of c dc? Well, by definition, that's the integral from c to d, f of beta of s, beta prime of s ds. What is beta of s? Beta of s is gamma of h of s. And what is beta prime of s? I see the composition of two functions, so by the chain rule, that's gamma prime of h of s times h prime of s. So that's what you see down here. Now, we use our integration by substitution factor. H of s is our t. So this is also our t. And there's our h prime of s ds, which will become our dt. So by integration by substitution, it's the same thing as the integral from a to b, f of gamma of t, gamma prime of t, dt. And that, by definition, is the integral over gamma, f of c to c. So the integral over beta is the same thing as the integral over gamma. Therefore, the complex path integral is what we say independent of the chosen parametrization. Now, so far we've been talking about smooth curves only. What if you had a curve that was almost smooth, except every now and then there's a little corner, like the one I drew down here? Well, for a piecewise smooth curve, so that's a curve where it's put together from finally many smooth pieces, where each piece starts where the previous one ends. Then one can show that the integral over gamma f of c dz is the same thing as integrating over gamma 1, adding to that the integral over gamma 2, adding to that the integral over gamma 3, and so forth, up to the integral over gamma n. I also want to introduce you to reverse paths. Given a curve gamma, defined in an interval from a to b, there's a curve minus gamma. And this is a confusing notation because we don't mean to take the negative of the gamma of t. It's literally a new curve minus gamma. So if you don't like this notation, call this gamma tilde or gamma star or something like that. So this is a new curve, or call it even beta. So there's a new curve also defined on a to b, and it's given by taking the original curve gamma, but instead of evaluating at t, we evaluate it at a plus b minus t. So if you take minus gamma and evaluate it at its initial point a, what you actually get is gamma of a plus b minus a, which is gamma of b. So the initial point of the curve minus gamma is actually the point where the original curve gamma ended. So in this picture down here, gamma ends at gamma of b, but that is the starting point of the curve minus gamma. Furthermore, minus gamma of b is gamma of a plus b minus b, so that's gamma of a. So minus gamma ends where gamma used to start. The curve minus gamma passes through all the points that gamma went through, but in reverse orientation. That's why it's called the reverse path. Now, what's the derivative of minus gamma? Minus gamma prime of t is the derivative of this function gamma of a plus b minus t. That's a composition of two functions. So we get gamma prime of a plus b minus t. That's the derivative of what's inside. But the derivative of a plus b minus t is minus 1. If f is a continuous function that's complex valued on gamma, what happens when I integrate it over minus gamma? The integral over minus gamma, f of c dz, by definition, is the integral from a to b, f of minus gamma of s, minus gamma prime of s ds. And then you can go through what I wrote down here to find out it's actually the negative of the integral over gamma, f of c dz. So if you integrate a function over a reverse path, the integral flips its sign as compared to the integral over the original path. Here are some facts about complex curve integrals. So as always, gamma is a curve, c is a complex constant, and f and g are continuous and complex valued on gamma. The integral over gamma of f plus g can be pulled apart, just like in regular calculus, you can pull the integral apart along the sum. So this equals the integral over gamma f of c dz plus the integral over gamma g of c dz. Furthermore, complex constants can be pulled out, and we've been doing this. So the integral c times f is c times the integral over f, and this one we just showed. The integral over the reverse path is the same as the negative of the integral over the original path. Now let's figure out how we could find the length of a curve. Given a curve gamma, how do we find how long it is? Normally you would take maybe a piece of yarn, lay it along the curve, then straighten it out and measure its length. But how do you actually do that? Well, suppose we take this interval from a to b and subdivide it again into its little pieces and look at these intermediate points on the curve, and we can approximate the length of the curve by just measuring straight between all those points. And the closer the points are together, the better the approximation seems to be. So the length of gamma can be approximated by taking gamma of tj plus 1 minus gamma of tj and the absolute value of that. If this sum has a limit as n goes to infinity, that is called the length of gamma, and if this limit exists, we say that the curve gamma is rectifiable or it has a length. Note that not every curve has a length. You could imagine that, even though it seemed that this piece was a good approximation of this curve here, as you zoom in really far, if you, zoom into a little piece right here, if you zoom into that, maybe there's a lot more going on than you actually thought, and it's a whole lot longer than you thought. And then if you zoom into another little piece, that happens again. So none of your approximations will ever be any good. If that is the case, the curve won't be rectifiable. But for us, most of the curves we deal with are rectifiable and have a length. The question is, how do we find that length? So we know it's given by the limit of these sums, but that doesn't really help, because you can't really go measure all these little distances and add them up. So is there a way to actually calculate the length of a curve given its parametrization? And there is. The idea comes by looking at the sum a little bit more carefully and applying a trick that we applied before. So we look at gamma of tj plus 1 minus gamma of tj, that's the line segment between consecutive points, and divide that by tj plus 1 minus tj, and immediately multiply by tj plus 1 minus tj. And we observe that this term here, if the tj's are close to each other, is roughly the absolute value of the derivative, gamma prime of tj. And this is my delta tj. As before, as n goes to infinity, this sum goes to the integral from a to b of gamma prime of t dt. In other words, the length of gamma can be found as the integral from a to b, the absolute value of gamma prime of t dt. This is true for any smooth or piecewise smooth curve gamma. For smooth or piecewise smooth curves gamma, you don't have to worry about the length not existing. Those all have a length, and it can be found in this way. Let's look at some examples. Let's go back to our curve gamma of t equals r e to the it. We all know what that looks like. That's simply a circle of radius r, and we even know how long that curve should be. This is the circumference of the circle. but that's actually calculated with our formula. We know that gamma prime of t is ri e to the it, and so the length of gamma is given by the integral from 0 to 2 pi of the absolute value of ri e to the it. That's my gamma prime of t right here, dt. But the absolute value of e to the it is 1, I has absolute value 1, so the absolute value of gamma prime is simply r. And so we're integrating r from 0 to 2 pi. R is a constant, and antiderivative is r times t. We plug in 2 pi, we get 2 pi r, we plug in 0, that's nothing. So the length of this curve is 2 pi r, and we knew that. The circumference of a circle of radius r is indeed 2 pi r. Let's look at another example. Let gamma of t be the curve t plus it. We looked at this curve before. Here's what it looks like. When t is equal to 0, it's at the origin. When t is equal to 1, it is at 1 plus I. And in between, it goes linearly. So here's my curve gamma. And I want to find out how long it is. And again, by looking at this picture, I can calculate its length because it is a hypotenuse of a triangle. Both of its legs have length 1. So the hypotenuse has length square root of 2. Let's see if our formula gives us the same result. Well, first of all, gamma prime of t is 1 plus I. And so the length of gamma is found by integrating from 0 to 1 the absolute value of gamma prime of t. So the absolute value of 1 plus I dt. What is the absolute value of 1 plus I? The absolute value of a complex number can be found by taking the square root of the real part squared plus the imaginary part squared. Both real part and imaginary part are 1. Together that adds up to 2, so square root of 2 is the length of 1 plus I. And so we're integrating from 0 to 1 square root of 2 dt. Square root of 2 is an antiderivative, which is square root of 2 times t. We're plugging in 1 and 0, and so we find square root of 2 as the answer. And that's exactly what we expected. This length right here is indeed square root of 2. Now this prompts a new definition. Suppose gamma is a smooth curve, f complex valued and continuous on gamma. We can find the integral over gamma f of z dz, and the only way this differed from the previous integral is that we always have to put these absolute value signs around dz. We're defining that to be the integral from a to b, f of gamma of t times the absolute value of gamma prime of t dt. So that's the only way in which this new integral that we're defining differs from the complex path integral. We call this the integral of f over gamma with respect to arc length, because this absolute value of gamma prime of t was related to finding the length of a curve. Let's look at some examples. The length of a curve gamma, we just found that can be found by taking the integral from a to b of gamma prime of t, absolute value dt. So in my notation, the function f of gamma of t is just the function 1. So there's f identically equal to 1. And then this length integral agrees with the integral on the right. But by definition, that is then the integral of 1 times the absolute value dz. So the length of gamma is the integral over gamma of the absolute value of dz. Let's look at another example. Suppose we wanted to integrate over the circle of radius 1. If you remember when we use this notation, absolute value of t equals to 1, we automatically assume the circle is oriented counterclockwise. And typically we choose the parametrization gamma of t equals e to the it, which t runs from 0 to 2 pi. So this is the integral from 0 to 2 pi, f of gamma of t, but f of z is the function z. So f of gamma of t is simply e to the it times the absolute value of the derivative. Gamma prime of t in this case is I e to the it, but the absolute value of gamma prime of t is equal to 1. So that's where this 1 right here comes from. So we're integrating from 0 to 2 pi e to the it. And then derivative of e to the it, we found that last class, is minus I times e to the it. We integrate that from 0 to 2 pi and find minus I times e to the 2 pi I minus plus I times e to the 0, and those terms cancel each other out and we end up with 0. Note that we could have also used piecewise smooth curves in all of the above. We would have broken out the integral into the sum over smooth pieces as before. Here's a great estimate. Sometimes it's impossible to find the actual value of an integral, but all we need is an upper bound. It's no bigger than some certain number. And this is called the ML estimate. Given the curve gamma and a continuous function on gamma, it can be shown that the integral over gamma f of z dz, the absolute value of that integral is bounded above by the integral over gamma, absolute value of f of z, absolute value dz. In other words, the absolute value can kind of be pulled to the inside. This reminds us a little bit of the triangle inequality. Remember, a plus b absolute value is bounded above by the absolute value of a plus the absolute value of b. This can be viewed in a similar manner, actually proofed in a similar manner. In particular, if you happen to know that your function f is bounded by some constant m along gamma, then this f of z would be less than or equal to m. So you could go one step further. It's less than or equal to the integral over gamma m dz. You could then pull the m outside of the integral, and you're left with the integral over gamma dz, which is the length of gamma. So if f is bounded by some constant m on gamma, then the absolute value of this path integral is bounded above by m times the length of gamma, which length L would be a good approximation for that. That's why this is called the ML estimate. Let's look at some more examples. Suppose we wanted to find the integral over the circle z equals 1 of 1 over z absolute value of dz. So the integral with respect to arc length. Again, we know the parametrization we're using is gamma of t equals e to the it, and we already showed that the absolute value of gamma prime of t is 1. So the integral of 1 over z absolute value dz by definition is the integral from 0 to 2 pi. This is my f of gamma of t, so 1 over gamma of t, so 1 over e to the it, times gamma prime of t, which is 1 dt. And antiderivative of e to the minus it is I times e to the minus it, evaluated from 0 to 2 pi. Again, the two terms that you get cancel each other out. The integral evaluates to 0. Next, let's look again at our path gamma of t equals t plus it. So again, that was the path from the origin to 1 plus I. We'd like to find an upper bound for the integral over gamma of the function z squared dz. Let's first use the ML estimate, so the second part of our theorem, which said that the integral over gamma f of c dz absolute value is bounded above by m times the length of gamma, where m is a bound on f on this path gamma. So for us, f of z is the function z squared. What kind of bound do we have for z values that are from this path gamma? Well, f of z is an absolute value, the absolute value of z squared. And the absolute value of z on this entire path gamma never gets bigger than this absolute value of 1 plus I, which is the biggest it gets in absolute value. But 1 plus I has absolute value square root of 2. So the absolute value of z never gets bigger than the square root of 2, and so the absolute value of z squared is bounded above by 2 on gamma. So we can use m equals 2 on gamma. We also know that the length of gamma is root 2, we calculated that earlier, and therefore using the ML estimate, the absolute value of the path integral of z squared dz is bounded above by m, which is 2, times the length of gamma, which is square root of 2. So it's 2 square root of 2. Let's try to also use the first part of that theorem to find an estimate, maybe even a better estimate, for the integral of z squared dz over gamma. So again, gamma of t is t plus it, gamma prime of t is 1 plus I, and so the absolute value of gamma prime of t is square root of 2, which is the absolute value of 1 plus I. F of z is the function z squared. The first part of the theorem said that the absolute value of the integral over gamma f of c dz is bounded above by just pulling the absolute values inside. So the integral over gamma, absolute value of f of c, absolute value of tz. Let's see if we can calculate that. So the integral over z squared dz is bounded above by the integral over the absolute value of z squared, absolute value of dz. By definition, that's the integral from 0 to 1. We look at gamma of t instead of z squared, and then we need to fill in absolute value of gamma prime of t dt. But gamma of t is t plus it, so we need to take the absolute value of that and square it, and then multiply with the absolute value of gamma prime of t, which is square root of 2. What is the absolute value of t plus it? Squared. Well, we take the real part and square it, the real part is t, and then we take the imaginary part and square it. The imaginary part is also t. So altogether, the absolute value is 2t squared, and that's what you see right here. And then we multiply with square root of 2, which was the absolute value of the derivative. The 2 and the square root of 2 can be pulled outside of the integral. We're left with the integral from 0 to 1 of t squared. And antiderivative of t squared is 1/3 t cubed, and that's what you see right here. We evaluate that from 0 to 1. When you plug in 1 for t, you get 2 root 2 over 3. When you plug in 0, the term vanishes, and so the integral has value 2 root 2 over 3. We found that the integral over gamma z squared dz is bounded above by 2/3 root 2. Now let me remind you that we actually calculated this integral earlier. We calculated its actual value as 2/3 times minus 1 plus I in the last lecture. Minus 1 plus I has absolute value of square root of 2. So if you put absolute values around this actually equals 2/3 times root 2. So the estimate we got was as good as it gets. It's a sharp estimate. It doesn't get any better. The estimate is actually an equality in this particular case. You will not always get an equality, but this example is set up to yield an equality here. So this doesn't get any better. You cannot improve this estimate because we found an example in which case equality is actually true. Next up is the fundamental theorem of calculus for analytic functions. We already saw it for real value functions, and we'll now be able to prove a similar fact for analytic functions.